Hi, welcome to session 12. In this session I'm going to be looking at putting some of these principles that we found out about how the glider flies, how it behaves, into practice, so practical applications. So first of all, we're going to look at soaring flight. Obviously it's possible to launch a paraglider or a hang glider, take it off and fly down easy enough, but when we're using in moving air, if we can find air that's rising, as already established, we can have soaring flight. By soaring flight, I just mean maintaining or being able to gain height and obviously therefore maintaining your time in the air. So we've already established that a glider is just that, a glider. It's always moving forwards and downwards through the air mass. So the only way we can stay up, short of putting an engine on our back, is to find some air that's going up faster than we're going down. So our minimum sink rate is around about 1.2 meters per second. Obviously, it all depends on your wing loading and what model of glider you're flying. That is something like 5 kilometers an hour or 3 miles an hour. So what we need is at least 3 miles an hour of vertically moving air in order to stay up. Now, in practice, we need quite a bit more than that because, you know, our sink rate increases every time we turn, and it's almost impossible to find air that's going up completely vertically. There's always a horizontal component. So that's the trick, just to find air that's going up. So let's look at that. Ridge lift is the first place that we might look for it. So basically the air mass hits a hill and is deflected upwards. I'm sure you're aware of this. The steeper the slope is, the greater the vertical component of the air. So if an air mass hits a shallow slope, it may not have a very big vertical component, so you might have a 12 mile an hour wind but only 3 or 4 miles an hour worth of lift, so difficult to stay up. On the other hand, if it's a vertical cliff and it's a 12 mile an hour wind, you might have 10 miles an hour worth of vertical component. So it's never going to be 100%, but it is short of a wind tunnel pointing upwards, I suppose. So the key to ridge soaring is to find that lift. So it's been able to visualize what the air is doing on the hill, which obviously means the steepest bits, and of course steep not just in terms of physical steepness, but how fast the air has to climb. So the most into wind as well. So that's just a little bit about you know, identifying. When you're doing ridge lift, that's what you're doing all the time. You're looking at the shape of the hill, thinking where is the lift going to be strongest. So using ridge lift, this little diagram here, it's a cliff, but it just gives you an idea. Obviously, you already know about the rotor or the turbulent zone behind the edge. So what we're going to focus on here is the lift band. When you have a lift band, the air is trying to carry on in the same direction. It's sort of forced out of its comfort zone by the ridge. So what this means is that the strongest lift is where it has no choice. So it's in front of the steep bits going upwards. As soon as you get above the top of the hill, it starts to flatten out again. So the shape of the hill has a big effect. If it's like a concave shape, it will throw the air upwards, if you see what I mean. Imagine something being spilled up the front. But if it's convex, it'll start steeply and then try to shallow off quite quickly. So we're looking not only for the steep part of the hill, but also the shape of it. It gives us a good idea of the shape that the lift band is going to take up as well. All right, so we want a hill that is large, just so we have a lot of room to play around in, steep as possible and into wind. And that's concave. Want to have the best slope above the crest. A convex slope, so where it's steeper near the bottom, like the South Downs for example, you often find that the best lift is just above the middle of the ridge or even further out above the foot of the ridge. So sometimes that means it's possible to soar a ridge, but you still can't get high enough to land back on the top again. So it's just identification of that. Bowls and spurs have a very important effect as well. With a bowl, you can work out where the lift is going to be most directly on or where it's been focused or intensified by the bowl. And with spurs, you'll often find that the, or if you like, a convex on the horizontal plane, that the air is spilling around the sides and therefore it's not very efficient. Okay. Not only the hill itself, but the aspect, the upwind situation is also important. For example, there are quite a lot of good flying sites which are actually a very small steep ridge, but what they are is on top of a long sloping bit of terrain that goes up to it. So if the air is already moving upwards, albeit quite slowly in terms of vertical thing, then that last little kick can produce quite a strong lift band. Equally, if the land is sloping down towards your hill and then there's a little hill, the lift tends to be much poorer. And that is just irrespective of anything else that's in front anyway. Even hills that are some miles away can have an effect by generating wave, all kinds of stuff. If it's completely smooth out in front, like flying on the coast, then you tend to get a nice laminar flow. But there we go. So that's ridge lift. Thermal lift. Sometimes obviously the two are mixed up together. So thermal lift. First of all, thermic conditions. We have to identify what thermic conditions are and where we're likely to find thermals. So there was a session in weather all about lapse rates and so forth, and RASP forecast, which gives you an idea. But essentially you need warm air generating, warm sun generating some heat and cool, relatively cooler air. So the ground gets warm while the air is cool, and then you get convection. When you get convection, there are a number of ways to tell. The first and most obvious is clouds. You get little cumulus clouds marking the top of the thermals, and that's great because it means the thermals are getting to dew point, hopefully at a reasonable altitude, and should be usable up till then. Another good indicator of thermal activity is the way that the air behaves. If you imagine you get a great big thermal going off in one spot and there's a light wind, what will actually happen is as it goes up, it'll leave a lower pressure and the air then flows in to fill that space. So if you're on top of a hill and you've got a windsock and the windsock suddenly turns to one side, that tends to mean that a thermal has gone off to one side and the wind has been pulled in at that angle to fill that space. And the same happens, fore and aft as well. If you're on top of the hill and the wind suddenly dies, that might mean that a thermal is going through. And very often that happens, and then a moment later, as the thermal has gone past you, the wind picks up again. So it's a question of moving, windsocks or streamers around, or uneven wind, as it were, both in gusts and direction, a good indicator of thermal conditions. And of course, the associated turbulence if they're strong thermals. Other thermal clues. Probably the easiest one is obviously other people flying. If you see people flying down, the ridge lift is, say you've got a ridge a couple of 100 feet high and there's people flying around 150 feet above it, and then somebody starts to circle and go up, or birds circling, things like that are always good clues as well. So visual clues, and when you're ridge soaring as well, you use visual clues. Obviously you work out what you think the ridge is going to be doing, but if you can see someone doing well at one end of the ridge, that's obviously where the lift is. So take advantage of your fellow pilots. That's when we're on a ridge or we've got time that we're hanging around and looking at stuff. When you're actually out, already committed, and you're on cross country, clouds are your main indicator and you should be going for the next building cloud, but you can also look for thermal triggers on the ground. So what are these? They're anything that will disrupt the warm air staying stuck to the ground. So the first thing is things where it gets inordinately hot. So that's a car park, for example, or a slope which it happens to be pointing directly into the sun. So if you've got slightly sloping land and it's pointing more to the south and it's midday, that's where you're going to get more likely to get hotter air, and therefore you're more likely to get a thermal trigger. But those aren't the only mechanisms. There are also areas where the air is allowed to get hotter. The two of these, the first one is where something shelters that bit of air. So this can be the lee side of a slope or behind a row of buildings or something like that, where the air is protected from the wind. And therefore it has a chance to get hotter before it breaks away. The second, and you often get quite strong thermals from that situation because you've got a nice big warm patch of air. The other thing, conversely, is where the wind dislodges the thermal from the ground, and this usually happens where you've got an interwind ridge of some description. So essentially what happens is the wind is going along the ground and it generates a small amount of ridge lift, probably not enough to fly in, not enough to have a flying sight, but just the fact there's a little bit of vertical component there can be enough to give the bubble of warm air which is stuck to the ground a bit of a kick and get it started. So if you get all these things combined, if you get an interwind slope with the sun on it, then that's a really good thermal trigger. And you often find slopes, there's bits going in and out, some of it's covered in forest, some of it's covered in rocks, and you find the rocky bit that's into the wind is where the thermals always come from. Of course, because we fly a lot of sites over and over again, the local pilots soon figure out where the best spots are for thermal triggers. But when you're on cross country, you have to look at that down and work it out for yourself, do a bit of thinking while you're airborne. Okay, so that's thermal triggers. An experienced instructor, my acquaintance I had him chatting to a group of his students a while ago, and he was saying, well, a good way to visualize where thermal's going to come off the terrain is if you imagine a relief map, so a little map, with all the relief, in 3D map, and you cover it in treacle, a bucket full of treacle, and then you turn it upside down. Everywhere the treacle drips off is where the thermals will come from. So off the tops of peaks, off the slopes and so forth. And obviously, it's not quite as simple as that for the reason I've just said, because you've got the wind in one direction and you've got sun maybe shining on more on one bit than another. But essentially, that is how it works. He teaches in the Lake District. Hi, Gordy, if you're watching this. So obviously, it's a hilly area. If you've got flatlands, then you're much more dependent on things like differences in the colour or the type of vegetation on the ground. Okay, so that's thermal triggers. Worthwhile spending a little bit of time thinking about those. The diurnal cycle, what's this? It's basically how things change during the day. So I have a little diagram for that I'll get to in a moment. And finally, of course, clouds. I mentioned cumulus clouds mark the top of thermals, but it doesn't just start there. If you have very small wispy cumulus clouds, it tends to mean that the thermals underneath are weak because there's not a great deal of water vapour being pushed up. Not necessarily, it can be because the air is very dry, but usually a weak or sort of wispy or not very deep cloud indicates a weak thermal. The other way around is you get a towering cloud where it's really high. If it's thousands of feet deep, then obviously by definition there must be a large amount of air and a lot of water vapour going up and reaching dew point there, so it's probably a strong thermal underneath. Clouds form and then they build and then they decay as the warm air feeding them dries up as they drift along. So the shape of the cloud and how it looks can give you a few clues as well. If you look up and it's just going milky above you, and then you look a couple of minutes later and it's quite a thick cloud, that's great because that's at the building phase. If you start circling up to a quite well-defined cloud and it kind of goes raggedy round the edges and starts getting thinner, that probably means that it's decaying, and therefore it's not such a good bet. And of course, thermals do actually have a finite life. They heat on the ground, they go up either as a common column or a series of bubbles, but it does mean that there's a bottom to them. And of course, they're going up faster than you're going up because you're gliding downwards, as we established. Therefore, it's easy to get left behind. You can often go under a cloud that looks fine, and above you there's a thermal, but there's nothing where you are. So it's a question of being lucky with your timing as well. So I mentioned the diurnal cycle, the air mass changes. So to put these in, clouds, basically, as the sun gets higher, heat the ground more, the thermal activity gets stronger from sort of mid-morning onwards. Obviously, it all depends on the time of year, how much heat, the latitude that you're at, all kinds of things. But as a general rule, it gets hotter during the day, the thermals get bigger and more powerful during the day, and the cloud base tends to rise as well. As this happens, the wind, certainly wind that's associated with thermal lift, gets stronger. So what you tend to get is weak thermal activity in the morning, gradually building, becoming more powerful, and in some places where it's hot, it can get really quite turbulent in the middle of the day. There are parts of the world where in the middle of the day in the summer, you don't fly because it's just too rough. And then as the afternoon wears on, it's a gradual decline. It's kind of this whale tail, really, and it gradually declines and gradually gets smoother and smoother. But interestingly, the cloud base, as the air is getting drier during the day, continues to rise. So very often pilots will get stronger thermals early on, and later on they get weaker thermals, but they will go a little bit higher. Base tends to be a little bit higher. So that's basically the diurnal cycle. I call it diurnal as if it's in a day, but it's not as simple as that. What can happen, and does frequently, particularly in the spring in the UK, is the sun comes out, shines on the ground, a lot of thermal activity, a lot of clouds build up. The clouds then block out the sun. It gets cooler again, then the clouds dissipate, then the sun comes out, and then the whole thing happens again. So you can have this cycle more than once in a day. Once it's overdeveloped, that is, once the clouds are starting to fill sort of 75–80% of the sky, there's not so much radiation reaching the ground and it kills the thermal production. So when it's a very active day, funnily enough, even though the thermals are stronger, it can be worse for doing long cross countries because you haven't got so much time until the whole thing fills in. Okay, so actually using rising air. It's a question of staying in the lifting bit. It's as simple as that. So, first of all, it's about the speed to fly. and that is if you're in lifting air, fly at minimum sink. Simple as that. However, if you're not in lifting air, if the air is sinking or you've just left a thermal, quite a lot of pilots tend to carry on flying at minimum sink on the grounds that they stay higher for longer. But it's a bit of a false economy because you will be in the sinking air for longer. So as soon as the air is sinking, you should be at trim speed, or if it's sinking hard, you should be on your speed bar to get out of there. Certainly in competitions, pilots tend to be either climbing at min sink or on the speed bar pretty well. It's usually one or the other. When to turn? It all depends on the strength of the thermal and the turn radius of your glider, but it's a very rough rule of thumb. When you turn, it's going to take you about 3 seconds or something like that to initiate a reasonable turn. Therefore, if you hit the thermal and you go, beep, 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 it starts to rise, I would tend to go for the 3 second rule, which is 1 and 2 and 3. If you're still beeping at that point, start your turn. How hard you turn depends on how strong the thermal is. If it's a bit weak, and obviously as you know, when we bank up it's less efficient, we reduce our sink rate, you might want to float around in a big circle. If it's a strong core, you want to get banked up and stick with it. Strong cores also, because they're going up faster, will also leave you behind at the bottom faster. So it's worth, you've got this race to base, as it were. You have to get as high as you can before the thermal dissipates. So very often in a strong core, you want to get yourself banked up, wound in. Paragliders and hang gliders are actually pretty efficient up to about 45 degrees. You have to actually bank up really steeply before you start losing much of your efficiency. So there you go. But that varies entirely on the circumstances. And of course, I'm talking about the UK's standard thermal. Sometimes they're different. Sometimes you have places with huge thermals. Sometimes you have different cores. You have a bit of lift here and a bit over there. And you have to sort of feed your way around all of them. But anyway, so how tightly to turn? Yeah, strength of the thermal will determine that. The race to base I've mentioned. Don't hang about. If you've got good lift, stick with it. Go with it. Otherwise, you'll get left behind. I've been in a situation where I've seen someone thermaling, slotting underneath them, absolutely nothing. Thought, blast, I missed it. Flown away, someone's coming underneath me, whoop, they've gone up as well. So sometimes they're bubbles with gaps in between. Luck of the draw, really. When to leave lift? Many years ago, when I was an inexperienced hang glider pilot, there was a guy who was one of the first cross-country pilots, if not the first, in the UK, called Bob Calvert. And Bob was brilliant ex-sea pilot. And I remember an inexperienced pilot, not me, but somebody else at a competition, saying, Bob, how do you go so far cross-country? And he said, well, I just don't land. And it sounds very trite, but there's a big element of truth to it. If you're in lift, unless you've got a cast iron guarantee that there's better lift somewhere else, then it is almost certainly not worth leaving it. You should stay with the bit that you've got. All right, if you're going up very slowly and there's someone very close to you is screaming up, then fair enough, it's a different situation. But generally, you stay in lift. And there's two reasons for this. The first thing is, paragliders in particular have frankly quite a poor glide, so you can lose a lot of height very quickly trying to find somewhere else. But secondly, wherever there is lift, there is sinking air around it. When you take 1,000 tons of air and you hoik it upwards at 500 feet per minute, all the air, another 1,000 tons of air, has got to slump in and fill the space. So if you fly out of the lifting bit through the shear line into the sinking bit, you could lose quite a lot of height quite quickly. It shouldn't sink as fast as you've just been going up, but nevertheless you will sink. So if you stay with it and you so hang around at cloud base or just keep working your lift until it dissipates to basically nothing or virtually nothing, then when you leave, you'll only get sort of standard sink, if you see what I mean. So you'll just start to glide as if it's still air. So that's the theory. It doesn't always work perfectly like that, but the bottom line, if you're in lift, unless you're in a race or somebody is, I say got a cast iron guarantee it's better over there, then never is the short answer. Just stay off the ground. Okay, vectors and headings. Normally we take off into wind, but as soon as we start flying on a ridge or thermaling or whatever, or we're tracking on a cross-country thing, we're flying with a crosswind component of some description. If we're lucky, we can go directly downwind, because that obviously maximises our ground speed and therefore our distance. But very often what you will want to do is you will want to go there, but the wind is coming from over here, whether on a ridge or not. So why the picture of the river? Well, you might be ahead of me. If you wanted to paddle across this river, you point at the other side and start paddling or swimming, what's going to happen is you're going to drift down the river as you go. And it's the same with the air. The air is pushing you from one side. If you point somewhere and you fly straight at it, your actual track is going to be like this. So what we have to do is we have to make that track good in order to make the way we're going. So we actually point slightly upwind so that we're pointing that way, but we're traveling that way. Now, of course, when we're soaring a ridge, that's really handy. It means we get to the end of the ridge and we can turn and go back and cover the same ground we've just done, but instead of making a 180-degree turn, we're probably turning 90 or 100 degrees or something, because we're drifting that way and then we're turning and drifting back again. Very useful for top landings. However, you should be aware of this. When you set a goal and what have you, you have to change your heading very slightly to maintain the direction you want to go. So that's crabbing or tracking flight. And the stronger the wind is, or the more crossed it is, then the more you have to alter that heading to maintain the track that you want. Right, directional control. How do we turn? This is paragliding specific here, really. This seems really basic. As soon as you do your first day, you learn how to control a paraglider. You look, you lean, and you tug on the brake. Simple as that. So what's actually happening? Well, when we pulled, oh, sorry, I've gone one too far on there. When you pull down on the brake, what you're doing is you're adding drag, and therefore you are trying to make the glider yaw. You're also making the glider roll a little bit, because the drag there is pulling that wing down, if you like. So the other wing rises up and turns around. It's actually drag aileron steering, technically. So that's the way that it works, and it's quite inefficient. I had a student many years ago who drove a tank for a living, and he said, oh yeah, it's just like driving a tank. So what do you mean? He said, well, both the tracks are going, and when you want to turn, you just put a brake on one side and it chews its way around the corner. Not subtle, but effective. So it's basically the same. We're just adding drag in order to turn. We can make that more efficient by using weight shift. If we lean into it, we can bank the aircraft by using a bit less drag. And obviously we don't want to minimize the drag. You can overdo it with weight shift though. If you completely load one side, you see sometimes pilots, sort of step in their wing. If you unload the outside wing, it makes it more prone to tucking, and it becomes less efficient if you overload it. So somewhere between the two. So it's look, lean and brake is the best way to do it. You've got pretty efficient angle to bank. At about 30 degrees, you've only increased your wing loading by about 10%. By the time you get up to 40, 45 degrees, it's creeping up. By the time you're at 60 degrees, so you're really banked up, you've added a lot of loading. So it all depends on how strong the lift is you are in. But I would recommend that 30 to 40 degrees is probably where you want to be in terms of angle of bank to be the most efficient, unless it's particularly strong lift. Okay, so landing approaches we're looking at now. So this diagram here shows the approach window. So what on earth is that? This is just something that a lot of pilots do find helpful. When you're looking at a landing field, pilots tend to focus on the spot that they want to land on, and that's fine, it works pretty well. But in order to do an accurate landing, if you've ever seen a picture of an aircraft coming down, they have a glide path, and they often have these little sort of boxes that appear that they stay in, and we can use the same thing, the approach window. If you imagine a big window frame like this over the end of your field, quite an efficient way or a useful way for pilots to visualize is to post yourself through the window. So how do you know where the window is? Well, the bottom of it has to be high enough so that you clear any hedge or boundary or whatever, and you're into wind with your wings level. So it might only be, 30 feet off the ground or something like that. The top of it depends on how long the field is. Obviously, if it's a huge long field, you can fly through a wind at 200 feet and you can still keep gliding in a straight line on your final approach without turning. So that decides it. The headwind depends as well. Obviously, you've got a headwind that again makes the window higher because you've got a steeper glide approach. And the width is the width of your field. So if you imagine this big frame in the sky, and you can make it, whatever you like, instead of looking at the ground, look at the frame, which is aligned into the wind, not so the field, and post yourself through the middle of the frame. You might find that a useful technique for ensuring you get in the right spot. The reason I'm very keen on this is I used to take people flying in a site called Epidavros in Greece, and there was a narrow beach. and people would come on, they'd turn over the sea, and then we'd think, oh no, they're going to go in the sea, or they'd be frightened of the sea, so they'd turn over the land and have real problems. And as soon as we gave them an imaginary frame over the end of the beach, everybody managed to land on the beach for some reason. It's just a question of posting yourself through that. It was pretty narrow, but it works for any landing field. So you've got two versions. You can do the sort of S-turn approach I'm showing here, but it works just as well if you're doing a constant aspect approach. Makes it easier to visualize. It's not about the touchdown, it's about the approach. So here we are. This is a standard aircraft circuit approach. So if you're flying any kind of powered aircraft, and you can do this with a glider as well, if you fly downwind, then you do a crosswind leg, and then you turn into wind. So the actual names, sorry, are downwind, base leg and finals. I'm probably aware of that. So that's just how an aircraft would normally land. They get their wings level into wind and then slow down, do their flaps, put their wheels down, whatever they need to do. So that's a standard aircraft approach. Now, because that doesn't work all that well for us, because we can't put ourselves in a fixed position, because if we get onto finals and we're a bit low to get through the window, we haven't got any power to put on. So we do a slightly different one. We use the constant aspect approach. And the constant aspect approach is the same basic principle. You fly downwind, so you're flying downwind parallel to your landing direction. You can look down, you can check the windsock, make sure you are flying downwind, not upwind, and then you basically hold your angle the same, the constant angle. So it doesn't matter what the angle is, depends on the wind or whatever, but it basically, if your landing field is going up relative to your field of vision, then you're getting a bit low. If it's going down, then you're climbing, as it were. So you just hold it level and you use your brakes to turn and maintain the angle, and obviously turn round until you can post yourself again through the approach window. So that's the constant aspect approach. Use it on all alpine sites, you have to really. Everybody else, because it's basically a circuit, everybody can slot in behind each other as well, which is much better than S-turns where you're in everybody's way and you have to make big turns and look over your shoulder to see where you are and all that. This is a much more effective system. Can't always do it on a small hill or a windy place in the UK, but if it's a large landing field or you've got reasonable height or you're on a cross country, this is the way to approach the landing. So that's the constant aspect approach, so called because of the angle that you try and maintain as you go around. Top landings now. So here's a little thing here. You've got different ways of top landing. So I'll look briefly at this diagram. Which is the best way? The answer is you can use any of them to top land, but assuming this diagram, it's sort of slightly exaggerated really, we'll start out with C there. So glider, the yellow glider C here, what he's doing is making a 180-degree turn, and in the middle of that turn, as he's coming back over the hill, he's heading pretty well on a downwind leg, so he's pretty fast over the ground, and then has to make another 180-degree turn in order to land. So there's a lot of turning going on there, and he's going pretty fast downwind, which is not a great idea. If you've got a load of sink, you'd have to make that 180-degree turn pretty quickly, which is asking for trouble. Also, on the shape of the hill shown here, there's not got much space. If you've got a bit high, you'd fly over the end or overshoot. So there's a lot of challenges there. Okay, B is the 360-degree turn approach. And again, an experienced pilot who knows his glider and is familiar with them can do this fine. So he basically turns and goes all the way around. So again, he's going almost straight downwind at one point. And then he again has to make very nearly a 180-degree turn back into the wind. He's drifted a long way downwind using 360. So you'll see when he makes his into-wind turn, he's already over the lee side of the slope. So if he loses height there, he's going to struggle. Suddenly he's looking at landing on a downwind slope, or worse, in turbulence if he sinks very quickly. The other thing about doing a 360 is if there's other people soaring around that ridge, suddenly sort of hurtle back downwind through them is quite disruptive to the pattern. So A, which is the favoured system, is you basically fly to one end of the ridge, the downwind end. So if you see the wind arrow, he's over at the downwind end, then turn. He's only making a bit more than 90-degree, maybe a 100-degree turn, and then tracking, using tracking and crabbing flight. So he's pointing this way, but travelling that way, floating across. And then, if he gets a bit of lift, he can just carry on a bit further, because you can see the top of the hill has got some more room there to go at. If he loses a bit of height and starts to sink, he can just turn into wind with a 60-degree turn, pretty easy, and get his wings level to land. Also, he never goes right over the back of the hill. So you might not have all these factors on a hill that you're top landing, but basically you always want to do the interwind beat as your final, your base leg, if you like. And for that to be the case, you need to start at the end of the downwind leg. If there isn't a downwind leg, then it doesn't matter, come in either way. Eventually you'll become experienced, you'll have lots of height and you'll start doing 360s in and what have you. But the basic pattern for a top landing is to track in one way like that, which gives you the most options, if you like, to deal with changing situations, and it's the safest. Also, because it all happens more slowly, it gives you more time to think and it's a bit less fraught generally. So that's top landing approaches. Okay, that's all I want to do in that session. So it's some of the principles about knowing how your glider flies, tracking flight and all that sort of thing, and just applying them to real situations so that we can make the most of any lift or any soaring that may be available. Okay, I hope that's useful.